Hi, thanks very much, David. So yeah, I'm Ross Burton. I'm the Meta ARM co-maintainer by virtue of being the principal software engineer at ARM Limited. I've been around the Octa project for many years, also currently on the TSC. So just basically, this is why is my build so slow, and what can I do about it? So first, we'll get this SKCD cartoon out of the way. Sometimes slow builds are in fact a bad thing because we just do want to get on with work. There are many aspects to what makes a build slow and what you can do about it. Your build machine spec is a fairly big component, but also what recipes are built in what configuration and rebuilds and etc. etc. There's many aspects. First, most important tip, always share your share state directory and your downloads directory. The only reason to not share and reuse share state is if you're testing a build from scratch. Other than that, always share. You don't need a share state per distro or per target machine, and multiple builders can use the same caches as long as you set it up properly. The Yocto Auto Builder has 30 different worker machines all connecting to the same shared state and downloads over NFS, and it works fine. This is building multiple machines for multiple distros, and there's no collisions. You don't need to worry. Obviously, if you're doing builds inside containers, make sure the shared state and downloads cache aren't stored inside the container, because if you rebuild the container, they disappear. It's very, very sad when CI is set up and the shared state caches are inside the containers, so every run has to start from scratch. That's very slow and very painful. And obviously, if you're doing it in the cloud, very expensive. So we'll start with the actual build machine itself. People tend to ask on IRC, what's a good build machine? This is not an easy question. The easy answer anyway is the best you can afford. You possibly got a laptop, maybe your own, or maybe when you started at your job, your employer gave you a laptop and said, here you go, build on that. Laptops aren't great for build machines. You can do occasional builds on them, but they don't really have enough cores. The cores there will get hot very quickly and they very firmly throttle down. They probably don't have enough memory and they probably don't have enough storage. Basically, a proper desktop machine will be much better value for money. You can get mobile workstations, but they have their own compromises. I can do some real world numbers to demonstrate using this ghetto benchmark. So this is literally the script I've been using to get these numbers. Fresh clone of Pecky on the latest LTS branch, create a fresh build environment, run all the fetch tasks because we don't care how slow servers are on the internet. Some repositories take half hour to fetch first time. And then just time how long Core Misato takes to build. Simple, easy, and reproducible. So on my corporate laptop, this cost about £1,500 retail. It's got 8 cores, 16 gigabytes of RAM. It's a nice laptop. Yeah, I enjoy using it. Core Misato takes 2.5 hours from scratch. Yeah, that's not terrible. I've seen far worse, but it's not particularly great. If you switch out for a air quotes mobile workstation, so a pretty high powered laptop, the compromises here are that it's expensive. So these are £3,000. They are portable, but you wouldn't want to carry it to work every day. But you do get 16 cores and fast storage and 64 gigabytes of RAM. This is faster. These did a build in 1 hour 45, which is a substantial improvement over the previous benchmark. And if you need something portable-ish, it's a good option. However, if you just spend the money and get a proper workstation, then For example, this is a workstation I got to experiment with a few weeks ago. Yes, it costs about £5,000 retail. It has 32 cores, 64 gigabytes of RAM, lots of calling, lots of fast storage. That did a core image SATO in 27 minutes. The I/O is ridiculous, so it did a shared state build. So delete the temp directory and then rebuild in under a minute. This is a wonderfully fast machine. It's expensive, but also builds tend to be bursty. So, as a CI machine or as a central builder, which a number of developers use to do builds on, this is probably a worthy investment. So if anyone is still being forced to do builds on laptops, then work out your hourly rate and how long you spend sitting around and how long actually buying a proper machine would take to pay itself back. So my build machine wish list is basically quite simple. Plenty of cores, but not lots. Especially some systems, the more cores you have, the peak performance will drop. So because the average will be higher, but the single-threaded performance will be slower. So you will need to find that middle point. You need good cooling so they don't firmly throttle. Lots of memory. 32 gigabytes of RAM is a realistic minimum. If you're doing big C++ projects, which like to eat all the memory in the world, 64 gig is a realistic starting point. And for storage, SSDs over NVMe are just so much faster than everything else at the moment. I used to say if you've got slow storage, like a traditional spinning Rust hard drive, just buy loads of RAM and use a 10%. But NVMe stuff is now, well, £100 for a terabyte last week when I looked at Amazon. Just buy that, it's cheaper. And I/O makes a big difference. There's a vague rule of thumb that you want a few gigabytes per actual core in big builds. So, scale up your memory and cores together. Otherwise, you'll end up ooming as too many processes are invocated at once. So that's a build machine. So now we have a look at the first build to see if there's anything that's redundant or can be optimized. The basic theory of looking at a complete build is if you build less, then you'll build faster. Bitback-G, which stands for graph-is, will write a task dependency tree, which is useful for analysts, and also a file called pm build list, which is all the recipes that are going to be built. You can just have a look at this and see if there's anything unexpected. So this build list, the image, quilt, patch, sudo, tools that are needed to build, the kernel, that's fine. GCC cross, that's for cross compiler, yes, fine. GCC, that's the target GCC that runs on the image itself. This is unexpected. SATO shouldn't be shipping a compiler inside it. We do have a tool called oe-depends-dot, which can examine the task depends and identify why something is being built. So we run that, and it says that core image SATO depends on elf utils, and that depends on GCC. So we can have a look at the elf utils recipe. And here we have the rdepends for the elf utils ptest package. This is, ptest is the package testing. So this is on target QA tests. This depends on GCC and bin utils, so it's obviously building some code as part of the tests. Now, if you're not running the ptests, then you can just turn off all the ptest packages. This is a distro feature called ptest, just remove it. And this dependency and many others will disappear and your builds will be faster. Of course, we also do say, but it's probably wise to run the ptests. but you can maybe do it once a week, or if you're just doing local development and you're not doing them, you can turn them off. And these will knock out a large number of dependencies. Alternatively, maybe you've got a headless system and you don't have a display, but you notice that libx11 is being built, which is not useful. Looking at the dependencies, you can see it's dbus, which is pulling this in. And yep, the dbus recipe has a distro feature, which is respecting the X11 feature, and it can turn on auto launch of daemons under X sessions. Of course, if you don't have X running, then this is absolutely a waste of time. So always turn off distro features that you don't need. In this case, if you're headless, then X11 and Wayland will remove some dependencies. This is a list of all the distro features that are shipped in Pocky out of the box. If you're using Pocky or something derived from it, have a look through this list. There may well be features in there which you are not using. For example, Wi-Fi or Bluetooth. These can drastically increase dependency trees as stuff is enabled. And if it's absolutely useless, then don't worry about it. So that's basically a good way of looking at what goes into the initial build. So you can also look at the performance of the build. This is where the build stats class is useful. This monitors the build and will write a log of all the tasks that were run and how long they took and what resources they were using. It's really useful for spotting bottlenecks and tasks which are just taking far too long and should be optimized. It's a standard class, so just inherit it as usual and then do a build. You'll probably want to do it with a clean share state because you want to do the benchmark from scratch. When the build is finished, the build stats are written into your build tree. They're human readable, but not great on their own unless you fancy reading hundreds of files. Luckily, we have a tool. There's a fork of PyBootchart which can pass these files and produce the boot chart graphs that we all know and love. Time goes from left to right, and every task is on a new row. By default, short tasks are hidden, so they don't flood the view, but you can turn them back on if you need to see them. So hopefully you can just make this out. That's the chart from the workstation I was talking about earlier. Zoomed right out so you can see the entire thing. On the whole, it's got a very steep gradient down, which shows it's building fast, because lots of tasks are happening in a short amount of time. But there are some interesting regions I've highlighted. There's a solid yellow section near the top and what looks like a gap at the bottom. This is the yellow vertical section at the top. Every task has its own color. So the yellow section is do configure. So here we have a lot of recipes, all spontaneously starting to configure at the same point. Looking back in time, we see that libtool has just finished building, and a little bit of digging will reveal that this is autotools.bb class. It's got a number of build dependencies, and unfortunately, they all bottleneck. So autotools takes a while to bootstrap, and then once it's finally finished, everything that depends on autotools can start building. It's unfortunate in this case, there's not a huge amount we can do about this. We've looked at optimizing the build process, but it just takes the time it does. Autotools isn't known for being particularly fast. It's interesting to note that Mason was happily building recipes long before autotools had finished bootstrapping itself. So if you do have lots of custom recipes and they use autotools, then I do consider looking to something like Mason. It's just faster. The other interesting region was this big gap at the bottom. Just after Matchbox panel finished, there's a big pause, and then some more recipes finish and the image is built. This may be a large number of tiny tasks, which were just happening all in a row. And you can turn on the visibility of short tasks, but in this case, it's not. This tends to suggest there's a long running task previously in the boot chart. And if we scroll up, yep, we have Rust native. This took 11 minutes to build on the workstation. In this case, we actually had to wait 2 minutes for Rust to finish building before the rest of the build could continue. Luckily, as it's a native task, this doesn't get rebuilt that often, and there is work to make this faster. There's a patch recently to knock out one of the build stages, which would probably knock a minute off this. But this may just be something we have to deal with. It's going to get increasingly harder, especially as the kernel starts using Rust, but you may be able to remove Rust from your builds if this hits you. In this case, it's Sato. librSVG is used by Sato, and librSVG is written in Rust. So in our builds, you can't avoid it, but you never know. In yours, maybe you can. This is the same build configuration on the corporate laptop from earlier. Yeah, you can see the massive green spikes, which are Rust doing its build. But the overall gradient is a lot less steep. So it's just showing how much slower it is. But also you'll note that there are no obvious bottlenecks or gaps. Rust takes forever, 55 minutes on this build, but nothing bottlenecks on it. The build is fairly smooth and consistent. So, you know, that's good news, I suppose. One other useful part of the boot chart is at the top, there's overall system load. So you can see CPU usage, memory usage, and disk usage. There should be throughput, but it doesn't appear on my machine for some reason. This can be useful. You can see spikes or gaps and see what recipe is causing these problems. It's good for correlating and looking at the build. One small trick is that if your build's taking a lot of time doing IO waits, you can try inheriting the RM work class, and I can imagine Richard wincing right now, and then do builds on a partition with a slow file system commit time, like several minutes. The theory being that if you can do a build and then delete the build before it actually gets onto disk, then you've reduced the amount of IO. But alternatively, get a better disk. Modern disks are very fast, and it makes a massive difference. So yeah, if system utilization is something that's interesting, then I do recommend Randy's talk later today. He's going to be talking about using the prop pressure file to monitor system load, which can help amortize the build and keep things faster. Next, I'll talk about optimizing rebuilds. Yocto is fairly unique. Unlike most distributions, we rebuild recipes automatically if there have been changes. This has advantages. We don't need to manually rebuild when there's dependency changes. We know the system is always rebuildable, and we know that you can always rebuild from scratch. Ask a friendly distro engineer when they last bootstrapped Red Hat, for example, and see they don't. The downside is this does take time, and rebuilds can be pointless. However, there is a way to build a lot less. We can avoid many of these rebuilds by using the hash equivalency server. This does require reproducible builds to be enabled, where building the same recipe twice results in literally identical outputs. This is always enabled in Langdao, but is an option in Dunfell. Very quickly, I'll explain how this works. So that's a rough overview of the task's process through BitBake. A task has its inputs, so the dependencies, any variables, the actual task steps. These all get hashed together into a task hash. This is what is looked up in the shared state. So if it already exists in shared state, then that object is unpacked and the task is done. If it doesn't, the task is run. The output is generated, and then that is put into shared state for next time. However, there are many inputs where the output is the same. If I patch a library, everything that links to it will get rebuilt. But if that library is being dynamically linked, then the binaries won't change. Hash equivalence is a way of saying that these two different task hashes actually produce the same output. So those two input hashes are the same. When hash equivalency is enabled, this task hash is looked up in the hash equiv database first, and that may return a new hash that is actually the same output. And that can potentially be looked up from shared state. When a task does still need to run, it will be the output will be updated into the hash equivalency database, and then that will keep track of what input hashes produce the same output. So future builds can be optimized further. The result is that builds with hash equivalency may start by saying, I need 2,000 tasks to be executed. But as pieces are built and found to be equivalent, they will all be taken from shared state instead. For example, in this build, when it started, it wanted 972 shared state objects. All I did was make a change to autoconf native to make it rebuild. It finished rebuilding autoconf, realized that the output is actually the same. So it says the unihash changed. The hash equivalency said, what you've done has already been built. And then a pile of tasks were marked as saying they became valid. Suddenly shared state is available after all. And it just went straight down to building the image. So by the end, it started saying it needed 900 objects. It rebuilt a few of them, and then 3,000 tasks didn't need to happen. That's a very high level and probably quite wrong impression, but that's roughly how it works. Basically, for faster rebuilds, turn on hash equivalency. It mitigates most of the downsides of automatic rebuilding. It's not enabled by default yet, but Pocky does turn it on. And these two lines are how you do it yourself. There is a caveat. If you're sharing shared state between multiple builds, you also need to share the hash equivalency database. So you run a persistent hash equivalency server. Setting this up properly is probably which probably should be a session on its own, because there's some complications if you're doing it at scale. You can also have Bitbake read from a centralized read-only hash equivalency server and share state mirrors in a corporate environment, for example, which is very useful if you have a central machine that does nightly builds of your product. Someone else who has a nightly machine doing builds is the Yocto Auto Builder. So if you're brave, the Yocto Auto Builder has a public shared state and hash server. So these two lines will let you use the Auto Builder's entire shared state and hash equivalency system. It's a little delicate right now. Last time I tried it, the rate throttling kicked in and it didn't let me connect half the objects. But it does work, and that's just an admin problem which we're working with. We're doing for 7 minutes left. Right. One last thing that's pretty well hidden, but can be incredibly useful. Locking the share state hashes. This is actually how the extended SDK works. So it's well tested. It's just not talked about often. Bitbake lets you specify the hash for a recipe explicitly instead of it working it out. So you can force Bitbake to use specific builds from share state. 99% of the time, you will not need to use this, but it can be useful. With locked share state, you can restrict the rebuilds to just the recipes you're working on, and everything else just will pull from the exact objects you've specified. Before I go any further, bug 13425. If you like the look of this, what I'm about to show you isn't particularly pretty. So if you like it and it's useful for you, then this is the bug to add proper tooling. Patches welcome. So the easiest way to specify what hashes to lock down is to ask Bitbake what the hashes are and just edit the file. One of the files bitbake-g writes out is the hashes. You can edit this and then include it in your configuration. In the glorious style of a diff, this is what we basically need to do. Bitbake-g will write a locked -6 file. We add a we unset the check variable at the top. By default, bitbake will abort if the hashes don't match, and we don't want that. And say I'm working on Python 3. Every time I touch the Python 3 recipe, Python 3 native will be rebuilt. Someone needs to be muted. A touch to Python 3 would change Python 3 native, which will cause RPM to rebuild, which will then repackage everything. This gets very boring very quickly. If we lock everything apart from target Python 3, then every build will take everything from shared state apart from the one recipe we are working on. This file then needs to be included into the configuration. So moving it to AutoConf works, and then just do a build. You'll get messages from bitbake telling you that recipes are being locked, and you will build a lot less. It's very useful in extreme circumstances. But if you find yourself doing a build and watching everything rebuild every time, even though it's absolutely useless, then this may be your savior. And with 4 minutes left, are there any questions? I can see a vast amount of chat on the Zoom. So I don't know if there's any questions that I can answer now, or grab me on email, ross.burton@arm.com, or I'm on our IRC, my nick's Burton. Thank you very much.